Welcome to the second last video in the gravitation topic. In this video, we're looking at Newton and Kepler, in other words, at orbits and energy. So we know from Kepler that orbits are elliptical. And we know from Newton that orbits are a result of gravitational attraction. From Newton's laws of motion, as well as from our everyday experience, we know that when we throw an object on Earth, it will always fall down due to Earth's gravity. So if we take a look now at an object that we throw horizontally, so we give it only an initial velocity in the horizontal direction, the path that the object takes as it falls to Earth due to gravity is part of an ellipse. So it's part of an orbit, but the Earth got in the way and stopped the orbit completing. If we throw it harder, we know that it will go further. So its path will still be part of an ellipse, a larger ellipse, but the ball will still be stopped by the ground. So if we increase our speed even more, we'll zoom back a bit so that we can see the curvature of the Earth. And we throw the ball harder still, so I'd say maybe at this point we're using something like a potato gun. We increase its initial horizontal velocity. So we can see now that as the ball is falling towards the Earth, the curvature of the Earth means that as the ball is dropping, the Earth is also dropping away from the ball. And from our point of view on Earth, all we see is that the ball has gone even further horizontally. And again, the path that that ball traces out is part of an ellipse. So if we increase our velocity even further, so we zoom out for the last time, and we'll pelt the ball this time as hard as humanly possible, actually probably significantly harder than humanly possible. I'd say by now we'd be using something like a rocket launcher. Then the ball is moving so fast horizontally that even though it is always falling down towards the Earth due to gravity, it's covering the horizontal distance fast enough that the Earth is curving down at the same rate that the ball is falling down. So the ball never hits the Earth, it goes into orbit. Or in other words, in this case, the velocity that we've given the ball means that the centripetal force on the ball is equal to the force due to gravity. So this velocity that we give the ball is called the circular orbital velocity or the circular orbital speed. So then the next obvious question is, at what speed will the object go into orbit? So I'll leave that one for you, and followed by a supplementary question: what is the total energy of an object in orbit if we assume the only force acting on that object is gravity?